Somehow I was recording before, but hadn't done anything. I guess we have a good recording of my board washing technique, wandering around the room, making random comments. But I probably won't even post that. Okay. I doubt everybody would find it useful. Okay. Got a paraboloid, x squared plus y squared minus a plus 5 equals 0. You can see that's a paraboloid. Just using its usual techniques. We want the region within the cylinder R equals 4. Now this is a polar coordinate notation. This is rectangular notation, okay? So I'm kind of mixing the two, but we want to then describe this region between the XY plane, above the XY plane, below the paraboloid, within this cylinder, okay? Now this R equals 4 cylinders, this cylinder radius 4, extending up and down on the plane, XY plane, an infinite cylinder, but we truncate it with this paraboloid and with the XY plane. Well, first of all, just get a picture, because you always want to sketch things, and a lot of people just want to write out equations and form. Sometimes they're right, some people got these right. But it's good to have a picture, okay? And rather than doing a three-dimensional picture, I'm going to take this, okay, x squared plus y squared minus c plus 5 equals 0 is just r squared minus z plus 5 equals 0, right? If we want to go to cylindrical coordinates, and we can solve for z, and we get z equals r squared plus 5. Well, fairly easy to sketch that. Here's r, here's z. Now, that is in 3 dimensions, but r could be in any direction down within the plane, your r axis for cylindrical coordinates. So it's just going to just kind of be the solid of revolution you get when you rotate this graph, okay, about the z-axis. Okay, well, r squared plus 5, well, that's pretty simple. That's just there's equals r squared plus 5. And down here is one side, r equals 4 this way, r equals 4 this way. So this isn't the scale because, of course, 4 squared is 16. 16 and 5 would be 21. Your y-intercept would be at 0, 5. Here's the intercept, right? And you go all the way up to 21 over here. So it's actually a much higher. Or we could have brought parabola down lower. Let's go ahead and do that. Just make it look. It's going to be about 4 times as high over here as it is down here. That's the schematic. There it is. And you can imagine revolving that and seeing what the thing would look like, right? It's like you got this paraboloid down here, okay? And you're looking at the region below the paraboloid. And it's fairly easy to sketch this in 3 dimensions, but you get the idea. Okay. So we could describe this as, first of all, 0 less than or equal to r less than or equal to 4, right? Makes sense. And then we don't have any restriction on theta. Okay. No, works for the whole plane. The cylinder r equals 4 implicitly includes all points with r less than or equal to 4 for all theta and for all z. So there we have it. And then C between 0 and R squared plus 5. Okay? That makes sense? And you want to get it down to that. Now, I keep talking about WebAssign. I hate the fact that they show you the picture of everything they ask you to do. Yeah, I just despise the fact that there's a picture for every set of equations, every function. Half and half would be okay. Showing you a picture for everything is giving you way too much and not forcing you to think through what these things look like. Okay? Just gives you a picture, you accept it, you set up your intervals, and you don't look at much. So kind of force yourself to maybe look at some of the problems in the back. Of course, they all have pictures too. I don't know. So I guess you don't really want people to learn to visualize things, but do your best to learn to visualize, get your own picture, make your own pictures, sketch your own curves. Learn that way. Okay. Yeah, just because you have software that'll make them pick pretty for you doesn't mean that you understand what you're seeing if you haven't constructed it yourself. So, and let me digress. One other thing. On the assignments page, I've given you 7 problems in section 615.4. The problems in the text. I can't seem to get WebAssign to even give me access to the problems in section 16 to assign any. Okay? It's just not there. It's probably something I did years ago, but there doesn't seem to be any way to restore. Okay? So, got the assignment out of your text for section 16. Okay? And that's really what we're talking about here. 16.4 as well as 16.5. How you set up integrals in 3-dimensional systems, rectangular, cylindrical. Okay, so here's a 3-dimensional region. This would lead directly to limits on an integral in 3-dimensional space. Right now, just dealing with how do we describe the region with inequalities? Does that make sense? Does this description make sense? Because you've done these problems on polar coordinates. So you should have a pretty good understanding of what you get in the plane. So in cylindrical coordinates, all you gotta do is add z coordinates and you have solid regions. Okay. 3-dimensional regions. In rectangular coordinates, it's pretty easy. In rectangular coordinates, well, in the XY plane, we got this circle of radius 4. So we got a circle of radius 4. Because that's what R equals 4 is. And of course, the equation for this circle is x squared plus y squared equals 4. Okay. Now, how do you describe the circle? Well, you describe that by negative x, negative 4, less or equal to x, less or equal to 4. Is because x goes to negative 4 here, goes to positive 4 here. And then for a given x, as we illustrated last time, and this is a picture you should be drawing. Okay, you just think of a typical partition. Given x, what are your limits on y? Okay. And You come up, and we came up with the same thing last time. When I said x squared plus y squared is 4, x squared plus y squared equals 16, right? I mean, this is a square radius. Make sure you understand that. So we get 16 minus x squared less or equal to y less or equal to the square root of 16 minus x squared. That would be this region here. Is that clear? If x goes from -4 to 4, and for any given x, y then would go as low as negative square root of 16 minus x squared, as high as the square root of 16 minus x squared. In another picture, you should be going this picture a little bigger. Is this set of two triangles here, where this is your radius, this is your x coordinate, this is the square root of r squared minus x squared, and this is the negative square root of r squared minus x squared. Writing that small. It's just a standard picture, a picture you draw over and over again, a picture you counter over and over again when you're doing common figures in 3 dimensions, okay? So there we have inequalities that describe where we can go in the XY plane. But then we have R and this restriction that was between the XY plane and this paraboloid just translates directly to 0 less or equal to Z less or equal to x squared plus y squared plus 5. Now, if we want to do an integral of some quantity or another, if we want to find the mass of this region, well, let me just work a Cartesian. To be explicit, have our partition R from R naught equals 0 to Rn equals 4. I'd be happier if I made this an upside down paraboloid, so it'd have a kind of a dome on top because it'd be easier to draw. It's hard to draw a hole in it. Okay. I could change the function, but okay. So it's like, okay, over here. Here's here's our circle of radius 4. And here is a ring corresponding to typical increment of R. Ith ring radius approximately equal to R sub I star. Width delta R sub I. That makes sense. Now, patient 0 less than or equal to theta less than or equal to 2 pi. Okay, well, you get I'll say partition this on the I R interval. Okay, you got some I R interval that corresponds to this whole circle. And you got theta naught less than theta 1. And it's going to be theta I0, theta I1, theta I M sub I equals 2 pi. Thought of why I've got an I on the M and why I've got an I in each one of these, but we're just looking at this ring. And we partition theta. So now we have delta theta Ij increment sample theta, theta Ij star. So that now this little increment dimensions. Delta Ri by Ri star delta theta by J. Now that follows what we did last time. Very similar to the way I drew it out, very similar to the way I notated it. Hopefully I wrote it a little more accurately, a little more clearly than I did last time. Now, partition 0 less than or equal to Z less than or equal to Ri star squared plus 5. Because your R coordinate here is Ri star. So how are you going to go before you have to stop? Due to this parabola, you're going to have to stop at Ri star squared plus 5. So, looking for so we now build a stack of these things. Very well thought. Get the idea. I say 0 equals Zij dot less than Zij1 less than etc. Less than Z P sub Ij equals Ri star squared plus 5. So now every point within this entire solid of revolution lies within one of these increments. For some R sub I star, for some I, for some J, and for some K. Does it make sense that that's the case? You don't really understand integrals unless you understand this. Okay? You're limited in what you can do with them. So it's worth understanding this picture and understanding the need for all of this notation. Now you get by glossing over some details. But the more details you gloss over, the more stuff later on you're going to have a hard time doing. And everybody has a hard time doing something like that. Okay? It's not like you're stupid if you run into trouble, because the field you're in has immense depth. And nobody's going to be able to go all the way to the full depth in everybody's going to encounter people that blow them away because they can do it. Okay? There's no shame in that. You know, I imagine there's some of us here that aren't Olympic class athletes. Myself excluded, of course. Okay, there's no shame in not being an Olympic class athlete. Okay, there's no shame in being a complete klutz. Okay, although a complete klutz that goes out and tries to compete with Olympic shaped athletes is going to look a bit like a fool. Okay, so know your limitations and don't stick your neck out too far. Okay, that's the picture. This is the reason that the integral, well, on the IJK increment, f of r theta z is f of r I star theta ij star z ijk star. Primary increment is r I star delta theta ij delta r I delta z ijk. Again, now why does z have three subscripts for r has one and theta has two? Well, because we decided the first thing we're going to partition is r. And we could have decided the first thing we're going to partition is theta. That would have been okay. We'd have come out with the same stuff, we would have had different numbers of subscripts. Okay, and then the last thing, once we got our position in the plane, we decided how far to go up to get to our parabola. Okay. So that the way this has been described, r is the last thing that we'll integrate with respect to, and z is probably the first thing. We're going to sort that out. All right. Volume of the increment is this. So I don't have room to write out what I need to write out, but I'll squeeze it in. So the contribution to the integral is, well, first of all, let me detect my IJK increment. That's what this says in blue, IJK increment. You might have trouble reading it there. Might have trouble reading it from anywhere, just need to know that. There it is. Okay. We selected our ith ring for R, an IJ ring for theta, an IJ increment for theta, and an IJK increment for R. Okay, contribution to the integral is what? It's just an L of RI star theta IJ star Z IJK star times RI star delta theta IJ I'm gonna write it. Integrated. Please follow this scheme. The IJK star theta IJ star delta Z delta R pi star. Again, that's pretty well squeezed in there. I'll write it on the paper. Well, I'm gonna write the sum. Then the total integral is approximately equal to this sum. But I'm not gonna have room to write out the equal. I'm gonna sum I equals 1 to n, j equals 1, m sub I, and from k equals 1, p sub I, j of f of R I star theta I j star c I j k star times the volume of this increment, which is R I star delta Z, and my delta Z and delta theta and delta R shouldn't have stars on. Delta Z IJK delta theta IJ delta R sub I. And this approaches then the integral. I would have to leave myself room to write some stuff in the integral. R is partitioned from 0 to 4. So R is going to go from 0 to 4. And we'll have a dr here on the end to kind of replace our delta R sub I. And then theta is in the middle. And theta is going to go from 0 to 2 pi, so that's going to be a d theta. And then C is going to go from 0 to R. Part of that R squared plus 5 of, okay, we'll have our dz here. We'll complete our volume increment with the R so that our R, dz, d theta, dr is the volume of this increment, of the typical increment. And then we have our L of R theta C. And there's our integral. Now, if we want to find the mass of the region, then F would be the mass density, right? Okay. In one of the examples that I think you saw before, but maybe not, maybe you're seeing it now. If F is the temperature at every point, okay, what do we get if we integrate this? Well, if we integrate the temperature with respect to volume and then divide by the total volume, we get the average temperature. So we extend the idea of average value, and you're going to see that. I gave you at least one problem of that nature in section 4. Okay. So if we want to find the average value of anything over this region, we integrate that thing over the region, whatever that thing is, F, R, theta, Z, and we divide by the volume, just like we get the average value of a function of one variable by integrating it over an interval and dividing by the length of the interval. Now you should have a good intuitive grasp of why that works, just in terms of pictures. Okay, so you want to think about that. But then that idea, if you have a good picture of it for functions of one variable, turns out it makes a lot of sense if you use it for functions of 2 to 3 variables. Integrate over an area, divide by the area, you get the average value. Integrate a function over volume, divide by the volume, you get the average value. And average values are really important. Okay. And often not that hard to estimate, and that's also a good way to check to see if your interval makes sense. If the values of your function are all between 2 and 5, and you integrate and divide by the volume and get 18, you know you did something wrong. Either you were wrong about the values all being between 2 and 5, or you did your interval wrong. In other words, you want to check your work against common sense. Okay. Now, does that example kind of make sense? As far as the description of the region, you probably need to sort some of the stuff about the sums. But of course, if you're doing approximations, this is exactly what you're doing. And for many functions, the best you can do is an approximation. So you better know how to set up an approximation and know what it means. Okay. Now with AI, you probably say, hey, approximate this, and says, here it is. Don't bother thinking about it. Just hope it works. No. Know how to think it through and know whether AI told you anything that makes sense. Okay. But we really need to start trusting AI, and then of course, people that get the interesting work will be the people that understand well enough to think critically about what AI is telling them. Teach a 5th grader to punch these numbers into a calculator and get a value. There's no value in being able to punch numbers into a calculator. Okay. But there is value in knowing the patterns that you get from the numbers, and you don't get that in your calculator. Analogy with AI. Okay. If we do the same thing in rectangular coordinates, what are we going to end up with? I'm going to ask you to write this out for rectangular coordinates. Can you write out these details for the integral and rectangular coordinates? They just practically, I mean, they correspond very nicely to the details you get in cylindrical coordinates, but it's worth spending at least 5, as many as 10 minutes on this. Okay, well, everybody pretty much wrote out the integral. You'd see a lot of this detail with the subscripts and the reasons for the subscripts and everything. And I do recommend that you try to understand that. It'll give you deeper knowledge. Okay. A whole lot. So there is some disturbing importance. I always like to use examples of trying to do a rectangular, solid and spherical coordinates. It's not for the faint-hearted. Or do a cylinder in spherical coordinates, which is quite a bit easier. I'm tempted to do that, but maybe not. Let me think for a minute. Okay, in spherical coordinates, um, okay, how would you describe the region that you get if you take a sphere and cut out the solid of revolution you would have if you revolve this region around towards the point? Okay, does that make sense? It's like you're pouring something, you know, you take a knife and stick it in there and then rotate it around to get a core out of it. If the radius of this thing is sphere radius A, you take this solid resolution. What's the volume of that solid resolution? I'll call that a time four. How do you set that up as a region in spherical coordinates? First of all, phi is the angle you make with the, well, the angle that you're, So if you've got a point out here, you go a segment from here to here, and here's rho, and here's phi, and you project this point down into the XY plane. Here's theta. Okay. And well, I labeled that just very clear. This will be your rho. This angle is phi. Okay. Now, if I draw the segment from here to here, or draw a segment from here to here, phi is pi over 6 either way. You don't have negative values of phi. Okay. Phi is just the angle with up here. You can go all the way down to an angle of pi over 2, but phi goes from 0 to pi over 2 for the entire sphere. Okay. And the entire sphere rho is going to go from 0 to A. You can't, rho is your distance from the origin. That can't be greater than the radius of the sphere, but it can be anything less than the radius of the sphere. Theta can go from 0 to 2 pi. In other words, you could take this point here, or this segment, and just rotate it around the vertical pole here, and you would get thetas go all the way from 0 to 2 pi, right? Okay. Just want to visualize that. But you want to look at the book's explanation and their pictures. They have good pictures. They just have too many pictures. Okay. Now, theta goes from 0 to 2 pi, and then pi can't go beyond pi, because no matter how close to the negative vertical pole you get, your angle with the positive vertical pole is not going to exceed pi. That makes sense? Okay, so what are your restrictions here? Within this core, your radius can go from 0 to A for any angle, right? Because no matter what direction you start out here, if you don't run into a restriction on rho until you get to the edge of the sphere at distance A, okay? So rho gets to go from 0 to A throughout the region. Your angle can't exceed pi over 6. If you went down to pi over 4, you'd be down here and you'd be outside this angle, you'd be outside that core. So the core is going to be described by 0 less than equal to rho less than equal to A, 0 less than equal to theta less than equal to 2 pi, 0 less than equal to phi less than equal to pi over 6. And there it is. Now you can set up partitions and you can integrate different functions over this region. But if you just want to get the volume, you're just going to integrate from 0 to A with respect to rho, 0 to pi with respect to theta, and from 0 pi over 6 with respect to phi. Then you got your rho squared sine phi for your volume increment. And we pictured that back a couple of chapters ago when we introduced polar coordinates. And if you do this integral, you get the expression for the volume. Okay? Suppose we wanted to chop off this rounded part here. It's kind of like an ice cream cone until we chop it off. So we take the ice cream cone, but we take the part on top, give it to somebody else, whatever. Go back. Yeah. Whatever. How are we going to do that? Okay. Okay, so what are we going to do if we want that core, except we want to flatten it off? Okay, well, got the pretty immediate response. I use cylindrical coordinates. Okay, cylindrical coordinates fairly straightforward. If your radius is A here, then this distance here is half of A, and this distance is half of A. And that's immediately because the cosine of pi over 6 is 1/2, right? So we could set this up as cylindrical coordinates. This is R. And this distance is A. This distance here is what A times the tangent of pi over 6, right? So for given R, got this little triangle here. Okay, and it's in the same proportion. The sides of this triangle in the same proportion to the sides of this triangle. So we'll call this Z. We can say that Z over R, well, it's just a tangent of pi over 6, isn't it? So that our region could be I'll get it right, yeah. A would go from 0 to 2 pi. R would go from 1/2 A. Z would go from 0 to R times tangent pi over 6, which is just, sorry, that's wrong. Z goes at most to A tangent pi over 6. And it starts at R tangent pi over 6. And I did leave myself room to write that. That says R tangent pi over 6. Let me write it over here. Better 0 less than take a less than 2 pi. 0 less than R less than 1/2 A. And R tangent pi over 6 less than or equal to A. And pi over 6. Of course, tangent pi over 6 is 1/2. So this will just be so your integral we'll go ahead and integrate theta last. Theta goes from 0 to 2 pi. R goes from 0 to 1/2 A. And Z goes from R over 2, A over 2. And we have our R dr d theta area increment down in the plane, z equals 0 plane. So that this would be our end. Okay. Well, hopefully you have enough to go on there. Email me if you have problems. I'll be checking it pretty frequently.